Okay, so today we start a new unit, Unit 3, the meaning of the derivative. Today's keeper is keeper 3.1, the average rate of change, and the definition of derivative at a point. All right, so the first definition I want to give you guys is the slope of the secant line. The slope of the secant line is f of x minus f of a over x minus a. This formula basically is just the average rate of change. You've calculated it probably since 7th or 8th grade. If you remember back when you first learned average rate of change, the formula that you used was y2 minus y1 over x2 minus x1. These two formulas are exactly the same. The slope of the secant line is just written a little bit differently, more of a professional, like grown-up way. But essentially, you're taking your difference of your y's, or your change in y, and you're doing the change of y over the change of x. So it's what you've been doing every time you ever calculated average rate of change or slope. All right, so our first example, again, just an old school example. You should already be able to do this, but we want to find the average rate of change of f of x equals x squared minus 5x, and we're doing that from 2 to 5. So the first thing I want to do is I want to set up my formula. So my formula says to basically do the change in y over the change of x. So I'm going to do f of 5 minus f of 2. That's my change in y. And then my change in x would be 5 minus 2. Now for f of 5, I got to plug that into the formula, so I get 5 squared minus 5 times 5, which is 25 minus 25, minus, and then f of 2 would be 2 squared minus 5 times 2. So again, I'm literally taking these points, right, these x values, and I'm plugging them into my formula up here. And so once I do that, it's just a matter of simplifying. So 25 minus 25 is 0. And then 4 minus 10 is negative 6. Since we're subtracting, that becomes positive. So I have 6 over 3, which is 2. In other words, my average rate of change, or the slope of the secant line, is going to be 2. Next, we have the derivative. So the derivative is different in that it's not the slope of the secant line, it's what we call the slope of the tangent line. So if you remember back in geometry, when we talked about tangent lines on circles, it was the line that touched the circle at just one point. So the derivative is giving us the slope of a line that's touching whatever curve or whatever function we have at a given point. It's not going through 2 points. It's touching at exactly 1 point. So in other words, it's the rate of change, it's the slope at that 1 point, not at a range or through a range of points. We also call that the instantaneous rate of change versus the average rate of change for the secant line. We call it the derivative, and we can denote that by several ways, but some of the ways is by y prime, f prime of x, or dy dx. All right, that's just some of the ways, but there are other ways that we can denote. So the definition of a derivative at a point, a comma f of a, or x comma y, is given by this formula down here. So we say f prime of a, or the derivative of f at a, is the limit as x approaches a of f of x minus f of a over x minus a. In other words, it's the same exact formula as the slope of the secant line or your average rate of change, except for this time we're doing a limit. Because we want our graph to approach a certain x value so that we're getting the actual tangent line instead of a secant line. You want to use this version of it because there are several different versions of the formula for a derivative, but you want to use this particular equation when you're given a specific x value to evaluate. So you don't want to just use it every single time, but if they say at x equals 3 or at x equals 5, then you want to use this formula. So again, just like reiterating all of that, your derivative is going to be your slope of your tangent line. So on this right hand side of the screen where it says slope of the tangent line, so over here, the slope of the tangent line again is the derivative. So if you notice, the slope of the tangent line is the same formula as the derivative, no difference. But what I need you to understand is that the question can be worded in different ways. I could say find the derivative at a point, or I could say find the slope of the tangent line. I could even ask you to find the equation of the tangent line. Either way, we're going to use the same formula where we have the limit as x approaches a, f of x minus f of a over x minus a. And again, this represents your instantaneous rate of change. So anytime you're finding the derivative, you're finding the instantaneous rate of change at a given point. All right, so our first example says find the derivative at a given point. So our function is f of x equals 2x plus 3, and our point is, or our x value of the point is x equals 1. All right, so I'm going to start with my formula, and again, I'm using this formula because they gave me the x value. They told me that x equals 1. So I'm just setting up my original equation of the formula. And then I'm going to start plugging into my formula. So for every time I see an A, I'm putting a 1. Okay? So basically that x equals 1, that is my A. That's what I'm approaching. So the limit as x approaches 1. And then up here in my numerator, I'm going to write f of x, which is the original equation. So that's the 2x plus 3. So that's f of x minus f of A, or f of 1. So what I'm going to do is I'm going to take this 1 again, and I'm plugging it into this x value, and I plug it into my formula. So from there, I'm going to simplify, and so I get the 2x plus 3. I leave that alone, and then I do minus 2 times 1 plus 3. Well, 2 times 1 plus 3 is 5, so that's minus 5. If I simplify a little bit more, adding the 3 and the negative 5, I get the limit as x approaches 1 of 2x minus 2. From there, I would factor out a 2. So I have 2 times x minus 1 over x minus 1. And then I can cancel out because this x minus 1 up top is the same as this x minus 1 on the bottom. So I can cancel those two values out, and I'm left with the limit as x approaches 1 of 2. Well, from last unit, you learned that the limit of a constant is that constant. So the limit as x approaches 1 of 2 is simply 2. In other words, the derivative at that point, or the slope of the tangent line at x equals 1, is 2. Next, we have another example, finding the derivative at a given point. And so our function is a little bit more complicated. We have a rational function, 2x plus 1 over x plus 2, and we're finding that at the point 1, 1. So again, I'm going to set up my formula. I'm going to plug in my f of x, which was the original equation. So this was my f of x. And I'm subtracting f of a. Well, they told me f of a this time. They told me that if I plug in 1 to this formula, I'm going to get 1 back out. And I can always test that. So if I plug in 1, I get 2 times 1 plus 3 over 1 plus 2, which is 3. So I get 3 over 3, which is 1. So I have f of x minus 1 over x minus 1, because again, remember, your a value is whatever you're approaching. It's that 1. It's the x value of the point. All right, so from here, I'm gonna try to simplify this by finding a common denominator in my numerator. And so I'm changing the 1 to be x plus 2 over x plus 2. Now that I have a common denominator, I can mush the fraction in my numerator together, and I get 2x plus 1 minus x minus 2. Make sure you distribute this negative over the common denominator of x plus 2, all over still the x minus 1. All right, so then I am going to simplify the numerator of my numerator. So here, on this step down here, I'm just going to simplify that, and I have 2x plus 1 minus x minus 2. That simplifies to x minus 1. Now what I'm going to do is a simple keep, change, flip. If you remember from middle school, we used to call that keep, change, flip. So I'm going to keep the numerator the same, x minus 1 over x plus 2, and I'm going to change it to multiplication instead of division, and I'm going to flip this denominator. So instead of x minus 1, I'm going to rewrite it as 1 over x minus 1. By doing that, I can see that this x minus 1 on the top cancels with this x minus 1 on the bottom, and I can simplify my fraction to be 1 over x plus 2. Now the limit as x approaches 1 over x plus 2, very simply, all I have to do is plug in the 1, and I get 1 over 1 plus 2, which is 1/3. So the derivative at the point 1, 1 is 1/3. Now, using those equations and being able to find the derivative at a particular point will allow us to find the tangent and normal equations of a line. So to find the tangent equation, basically you're going to find the derivative by finding the slope of the tangent line, and then you're going to input that derivative along with the point that you were given into the point slope form of an equation. You do not have to simplify the equation though. So once you plug it in, you're done, you're good to go. Now to find your normal line, and your normal line is basically the line perpendicular to your tangent line. To find that normal line, you basically are going to find the slope of the tangent line. So you're going to do everything to find the slope of the tangent line. But instead of using that slope that you find, you're going to find the slope of the perpendicular line to it. So if you remember, again, from like algebra 1, to find a perpendicular equation, you're going to do the negative reciprocal. So let's say my slope of the tangent line was 1/2. My slope of my normal line would be -2. So I'm going to do the negative reciprocal. And once I find that slope, I'm going to, again, put it into the point slope form of a line, and I'm not going to simplify it. I'm just going to leave it as is. For this example, we want to find the derivative of the function at a point, and then we want to use that to find the equation of the tangent and the normal lines. So again, I'm going to start by just finding my derivative. So I'm going to start with my formula. I'm going to plug in my f of x and my f of 3. In this case, this is going to be our a. So for f of x, I have x squared plus 2x minus f of 3 over x minus 3. And again, that's the limit as x approaches 3. Now, f of 3, we need to figure that out, but all I have to do to find out what f of 3 is plug that into my function everywhere I see an x. So f of 3 would be 3 squared plus 2 times 3. Now, simplifying this expression, I would get the limit as x approaches 3 of x squared plus 2x. And again, this piece inside, this f of 3 simplifies to 15. So I get x squared plus 2x minus 15. Now, factoring my numerator, I get x plus 5, x minus 3. And again, I can clearly see that the x minus 3 on top cancels with the x minus 3 on the bottom, and I'm left with the limit as x approaches 3 of x plus 5. Now, like we learned last unit, to find this limit, all we need to do is plug in that 3. So when I plug it in, I get 3 plus 5, which is 8. In other words, the derivative or the slope of my tangent line at x equals 3 is 8. Now to find the equation of the normal and tangent lines, I want to use my point slope form of a line. So just a refresher, the point slope form of the line is y minus y1 equals m times x minus x1. And we also know that our y1 is 15, and we know that because we found it when we calculated it over here for our derivative. All right, so for the slope of the tangent line, I'm going to do y minus 15 equals 8. Again, this 8 comes from the derivative that we just found here. 8 times x minus 3, and the 3 came from the x value that they gave us to start. So again, y minus 15 equals 8 x minus 3. Remember, I don't need to simplify it. I don't have to distribute. I don't have to add the 15 to the other side. It is customary and it's good form to leave your answer as it is right here. You actually don't want to simplify it, and I would prefer you not to. Now to find the slope of my normal line, I'm going to take that same equation I found for my tangent line, except for that 8, the slope of the tangent line, I'm going to change to be the negative reciprocal. So for my normal line, I'm going to have y minus 15 equals negative 1/8 x minus 3. All right, our very last definition that we need to know, or another way to write the derivative, is using velocity. So to find instantaneous velocity, like you would in a physics class, you can simply just find the derivative. This formula is actually the same formula. It's just rewritten to be more conducive to like a velocity type problem. You need to know each form of your derivative. So we had the first one we learned was the derivative at a point. This form here is the instantaneous velocity. Again, it's going to give you the same answer. It's just a different way of writing it. For this last example, we're going to see how the velocity formula works instead of using the derivative formula at a point. So in this example, it says if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet after t seconds is given by y equals 40t minus 16t squared. Find the velocity when t equals 2 or at 2 seconds. So again, I'm going to start with my formula. The limit as h approaches 0, f of a plus h minus f of a over h. Now this first part of my formula says f of a plus h. Now to find f of a plus h, everywhere I see a t, I'm going to replace it with a plus h. So I'm going to put a plus h here, and I'm going to put a plus h here. Now remember, your a is whatever value you're going to. So in this case, we're going to t equals 2. So my a is actually going to be 2. So instead of going with a plus h, I'm actually going to put in 2 plus h into my formula for my derivative. So again, that first part, every time I see a t, I'm going to put 2 plus h. So I get 40, 2 plus h, minus 16, 2 plus h squared. And then continuing with the formula, I have minus f of 2 all over h. Now what I need to figure out is what is f of 2. Well, f of 2 means to plug 2 into my formula. So every time I see a t, I'm going to put a 2. So I left the first part alone with my 2 plus h's, and then I said minus 40 times 2 minus 16 times 2 squared. Now what I want to do is simplify that numerator as much as possible. So I have 40 2 plus h minus 16 2 plus h squared. And this piece in my parentheses, I simplified that to my 16. All right, moving along, I'm keep simplifying my numerator, just doing it in steps. So the first part is I'm going to distribute this 40 into the 2 plus h, and that gives me 80 plus 40h. And then I left the minus 16, but I went ahead and squared the 2 plus h squared, and I got 4 plus 4h plus h squared. Continuing to simplify, I'm going to distribute that 16 in, and so I'm left with 80 plus 40h minus 64 minus 64h minus 16h squared minus 16 all over h. Simplifying some more, I'm going to clean up that numerator, add my like terms, and I get 40h minus 64h minus 16h squared. Now what I can do is I can take an h out of everything or divide everything by h, and that will leave me with negative 24 minus 16h. Now when I go to calculate my limit, h is approaching 0, so I plug 0 in for h, and I'm left with negative 24 feet per second.